All right. Does anyone have any questions?
No.
No? How about you, Greg? Do you have any questions for me? Well, then let's go ahead and get started with some problems from the chapter. So I'm going to change my share screen to include this camera, which always gets in my way. So I've got some problems written out here. And can you see these problems okay?
Yeah, looks good.
Thank you. Okay, so let's get started. Write an equation from the following description. The reactants are gaseous, NH3 and O2. The products are gaseous NO2 and liquid H2O. And the stoichiometric coefficients are 4, 7, 4, and 6 respectively. So the thing that we need to understand is that when you write a chemical reaction, the reactants are what you start with, and the products are what you form. So you normally write it from left to right. Reactants turn into products. And the arrow means produces, forms, or whatever. And so the reactants you normally write on the left-hand side of the arrow. So here we have the reactants are gaseous NH3. Now to denote that it's a gas, you use parentheses and a G. And O2, and you put a G there. And then they say that the products, so arrow, are gaseous NO2 and liquid H2O. And of course, the symbol for liquid is not the same as the symbol for gas, it's an L. And the stoichiometric coefficients are 4, 7, 4, and 6. So that means that you need 4 of these guys to react with 7 of these guys, to make 4 of these guys, and to make 6 of these guys. So these guys are, according to the problem, stoichiometric coefficients, but we can also just call them coefficients. Now, what do these coefficients mean? They mean that 4 molecules of NH3 is equal to 7 molecules of O2 is equal to 4 molecules of NO2 and is equal to 6 molecules of H2O. Now, we're not really saying they're equal to, we're saying it's equivalent to, meaning if you started with 4 molecules of NH3, you would expect to make 4 molecules of NO2. If you started with 7 molecules of O2 and used them up completely, you'd expect to make 6 molecules of H2O. But this also means 4 moles of NH3 is equal to 7 moles of O2 is equal to 4 moles of NO2 and is equal to 6 moles of H2O. Sometimes when you're writing the above, I leave molecules off. So this means you have 4 NH3s. You don't need to say molecules. And the reason I might leave that off is because molecules and moles sound so familiar that we might conflate them. And we don't want to do that. So if we ask the question, if we start off with 1.00 moles of NH3, and the question is, how many moles of H2O do we make? We would multiply by 6 moles of H2O for every 4 moles of NH3. And our answer would end up being, let's see, 1.5. 1.50. Likewise, if we start off with 1.00 times 10 to the 23 NH3s, and we wanted to figure out how many H2Os we would make, we would multiply by 4 NH3s for every 6 H2Os, and we see that this number would be 1.50 times 10 to the 23. So that's how we use coefficients in a calculation, if you will. And this is what the coefficients mean. So when we use these equalities, we can use any pair we want, any pair, and we can put either side on the bottom in the denominator and either side in the numerator, depending how we need to use it. So we good here with the equation.
Yeah.
Explain the bottom again where you use the number of moles. Yeah,
Right here,
no, right where your finger is.
right there.
You're right, and but then right below it, can you explain the equation right below it?
Well, this one I use this one I use this. See how we have 4 NH3s, 4
Oh, okay.
NH3s,
I
6
get it.
H2Os.
I got it, thanks.
So the point is, with the balanced reaction, it can be single molecules or it can be moles of molecules. Okay?
Right. So, for example, the second one, you would use it if I'm asking this as a question. You would use it if you're actually working with quantities of something, right? And then, well, I guess you could use both for they're both for quantity,
Yeah,
but
you can use them both. These are just very simple ways of using the coefficients.
Mhm.
And when you use the coefficients this way, we actually call that stoichiometry. So when we say stoichiometric coefficients, it means, hey, we can use them to convert. Okay?
Right. So in the second equation, the one that Greg was talking about, you're talking about like molecules of NH3. So it's kind of like, for example, a question would be like, if you have
How many molecules of H2O are you going to make from
NH3,
1
okay.
times 10 to the
Well,
20?
wouldn't the question be how many grams, if you had so many grams of NH3?
There's no grams here.
You can or can't? But I
You
could,
can?
but I
That's-
could convert it.
You can, but you'd have to first
Yeah,
do
but
it before the moles.
yeah,
You
yeah,
can-
all I'd have to do is convert it now and I could use it for, oh, gotcha, never mind.
You can use grams, but we're focusing on what the coefficients mean. The coefficients do not mean 4 grams reacts with 7 grams to give you 4 grams and 6 grams. Coefficients do not mean grams. And the proof is in the pudding. Here, if you have 4 grams and 7 grams, you're starting with 11, correct? 11 grams. And in chemical reactions, you do not get to lose grams. So here, if we say that we take 11 grams of stuff and we make 10 grams of stuff, we've lost a gram somewhere, and you don't get to do that in chemistry. So coefficients do not indicate grams. They indicate either molecules or moles.
Sorry to interrupt you. Thank you very much.
Yeah, we're good. So we'll move on and let's take a look at this next one. So the equation for the reaction of aluminum and bromine is Al plus 3Br2 gives you Al2Br6. This is an interesting reaction because of the following. Look at this formula here. It's a metal and a non-metal, correct? Which means it should be ionic. But when we write the formula of ionic compounds, we have the simplest ratio, and this does not have AlBr3, it has Al2Br6. Why? The answer is that's molecular. Remember, molecules have a molecular formula, which is the number of atoms in the molecule, and it has an empirical formula, which is the simplest ratio. So this is actually a molecular compound. Now, here, if we use 6.0 times 10 to the 23 of these, and notice they have molecules of Br2, so I'm going to go ahead and write that out. You never want to abbreviate the word molecule. And if we want to end up with atoms of aluminum, wouldn't it behoove us to multiply by something that has molecules of Br2 in the bottom and atoms of aluminum in the top? So where do we find that correct ratio? And the answer is right here. 3 molecules of Br2 and 2 atoms of aluminum. And so these are coefficients used to calculate how much of one thing from another. 3 goes into 6 2 times. 2 times 2 is 4. So the answer is 4.0 times 10 to the 23 atoms of aluminum. Now, why is Br2 called a molecule and why is aluminum called an atom? And the answer is molecules have atoms bonded together. And in this case, the bromines are bonded together. So that's why this is called a molecule. In this aluminum, the atoms are not bonded together with covalent bonds. So we call this atom of aluminum and not Al2 or anything like that. What are these 7 elements that come in pairs like bromine?
Hunkelbreath.
Right, Hunkelbreath. Hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine. So this is the kind of work for a problem like this that I would expect to see on an exam. Are we okay on this one?
Professor, I'm sorry, Tony.
Yes.
Most of the time they're going to tell us if something is solid, gas, or liquid, right?
Not always. For instance, it would not be common for someone to tell you the state of a element. You should know the state of the elements. And when you talk about the state, the assumption is at room temp. So what are the 2 elements that are liquid at room temp? And there's only 2, bromine and mercury. What are the gases at room temp? Well, the gases are hydrogen, helium, nitrogen, oxygen, fluorine, chlorine, and then all of the noble gases. So neon, krypton, argon, xenon, radon, and the one that's below radon, which is OG. Don't worry about that one. But these are all the gases at room temp. So which ones are solid at room temp? And the answer is the rest of them. So because these lists are smaller than the solid list, it's easier to remember the liquids. Next easiest to remember the gases, and then the solids are just the rest of them. So what is the state of uranium at room temp? Solid. What is the state of phosphorus at room temp? Solid. Okay. What is the state of carbon at room temp? Solid. Okay. So in answer to your question, you would be expected to know these 2, but not this one. And the reason you wouldn't be expected to know this one is because it's molecular and you don't know whether a molecule is a solid, liquid, or gas at room temp. If this were ionic, you'd say solid because ionics are solid at room temp, most of them. Are we good to go on this one?
Yes, I think so.
Are you good to go on that one, Greg?
Yep.
You can just give me a thumbs up if you want. That'll be perfect. Okay, now I need to put this off to the side. I'm trying to keep track of everything here. So let's look at this next problem. Okay, let's look at some key words here. To form solid MgO. What does that tell you about MgO? It's a product. And since it tells me it's a solid, I'm going to put a parentheses S. Now, this and this burns in air. The burns part is kind of like a word for a particular type of reaction. So we're going to put magnesium, solid, liquid, or gas. And the answer is solid. And it's not a Honkelbrief, so I'm not going to write Mg2. This burns in air to form 0.2 mole of solid MgO. What amount of oxygen is required for the complete reaction? Now, let's pretend that we did not see that part. If we only had this to begin with, what do we think Mg has to be reacting with to make MgO? And the answer is, since there's oxygen there, whatever it's reacting with, it better have oxygen. So here are our two choices. These are fairly common things in air, O2 and CO2. Why would we choose O2 and not CO2? And the answer is because if you had CO2 here, you would expect to have carbon over here. So no CO2. So oxygen's a Honkelbrief. So we put O2. And now we need to balance the reaction. For balancing reaction, there's a do and a don't. Here's the do. Change coefficients. And you change coefficients until the atoms on one side equal the atoms on the other. And I'm going to say more specifically, elements on one side equal the same ones on the other. That's your do. And we learned before that the coefficient is a number that goes in front of the formula. And here's the don't. It's a big don't. Don't change the formula. So when we look at this reaction, here's the don't. So here's the reaction from above. I want to make sure that the number of magnesiums on the left equal the number of magnesiums on the right of the arrow. One magnesium, that's good. Two oxygens, one oxygen, that's bad. So if I do this, I have two oxygens and two oxygens. Why is this a don't? I changed the formula. You do not get to change formulas. So let's bring the do down. So we're going to do the do. When I balance reactions, I like to start at the left and work to the right. Here we have one magnesium, and here we have one magnesium, so we're good. Here we have 2 oxygens and here we have 1. So I'm going to put a 2 here so that now we have the correct number of oxygens on each side. Now, when I put a 2 here, that changes the number of magnesiums on the right side. And I only have 1 magnesium over here. So how am I going to fix that? I'm going to put a 2 there. So I have 2 magnesiums, 2 magnesiums, 2 oxygens, 2 oxygens, and we're balanced. Another way to do the do on this side is as follows. I have 1 magnesium on the left and 1 on the right, and I have 2 oxygens on the left and 1 on the right. And I don't want to upset the magnesiums. I want to keep them equal to 1 each. So I'm going to put a 1/2 here. How many oxygens when we have half of an O2? 1. So we don't like coefficients that are fractions in our balanced reactions. So what do? We double everything. Now the default coefficient is 1. So how many magnesiums do we get if we double it? 2. What happens when we double half? We get 1. And what happens when we double 1? We get 2. So this is 2 ways of achieving the same outcome of a balanced reaction for this problem. And then lastly, they asked us in this problem, where is that problem? Oh, it's hidden beneath all my paper. 0.2 mole sample of magnesium burns in air to form 0.2 mole of solid MgO. What amount of oxygen moles is required? So this is what the problem is going to look like. And of course, we balanced this already. Now, I'm going to put moles of oxygen on top, 1 mole of O2, and moles of magnesium in the bottom, 2 moles of Mg. And we get 0.10 mole of O2. So for a problem like this, I would expect to see the balanced reaction and then this conversion right here. And it is important with these conversions to use the labels. So here, it's not enough to just use the unit, you have to use the label. What does this answer look like without the labels? It looks like this. And if you take a look at this, this basically says 0.2 moles is equal to 0.1 moles. And it doesn't make sense without the labels. So don't do that. Make sure you use the labels. Are we good to go on that one? Okay, we'll keep going. All right, Greg, we're good to go. Write balanced reactions equations for the following reactions. So here's a key word, production of ammonia. That means that's a product. By combining N2 and H2, well, combining would be another word for reacting or some sort of other word for reacting, like oxidizing or precipitating or something like that. So this is going to be a reactant as well as H2. And the ammonia is going to be a product. Okay, so when I balance reactions, normally I just like to work from left to right. 2 nitrogens here, 1 here, so I'm going to put a 2 there. 2 hydrogens here and 6 here, so I'm going to put a 3 there. Any questions about A, or are we good to go? Okay. The next one, you can see that we have H2 and what looks like H2O liquid, doesn't it? Nope, CO2. Excuse me, CO2 gas gives you CH3OH liquid. So, 2 hydrogens on the left and 3 on the right, correct? And the answer is no. There's 3 hydrogens right there, but right there is another hydrogen. There are 4 hydrogens here and 2 here. So how do we make this match? We put a 2 here because that means you have 2 H2s. Each H2 has 2 hydrogens for a total of 4. 1 carbon here, 1 carbon here. 2 oxygens here. Oh, I used the wrong formula. Do you see that? That should just be CO. 1 oxygen and 1 oxygen. So this one is done. Production of sulfuric acid by combining sulfur, oxygen, and water. So sulfur or sulfuric acid, what is the formula? Well, this is the sulfate ion in this upper right-hand corner. Sulfuric acid is H2SO4. So how do I know this is supposed to have 2 hydrogens? And the answer is the charge tells me. When you have a -2 charge, you're going to have 2 hydrogens here.
I see.
If you have a -3 charge and you want to make the acid, you say H3PO4, and this is phosphoric. It's the same thing for nitric acid. This is the nitrate. So nitric is HNO3. And notice the charge tells you how many hydrogens. So we're going to take sulfur, which we know is a solid at room temp. We're going to take oxygen, which we know is a Honkelbrief and a gas at room temp. And we're going to take water, which we know is H2O liquid at room temp. And we're going to make H2SO4. Now this, you don't have a clue as to whether it's a solid, liquid, or gas at room temp. So we're not going to worry about that. So let's go ahead and balance this. 1 sulfur, 1 sulfur. 2 oxygens, plus another one, 3 oxygens. And I have 4 over here. So what are we going to do? We could do this. We could put a 2 in front of this. And now we have 2 oxygens here and 2 oxygens here for 4. Now we have 4 hydrogens and we have 2 over here. So we're going to put a 2 here so that we have 4 hydrogens here and here. But when I put a 2 here, I changed the number of sulfurs and I changed the number of oxygens. And so I got to go back and fix something over here. Now we're going to leave sulfur for last and we're going to work on oxygen. We have 8 oxygens over here. And over here we have 1, 2, 3, 4 oxygens. So 4 oxygens versus 8 oxygens. How do we get 8 over here? And how do we do it so that we don't upset any other elements? And the answer is we got to change the coefficient in front of O2. Because if we do that, we don't have to go back and readjust hydrogen, which is what we'd have to do if we change this coefficient. So if we change this coefficient, we have to go back and forth and back and forth. And it's just a nightmare. I'm going to change the coefficient in front of this O2. So how do I get 8 oxygens on the left? By putting a number in front of O2.
3. 3.
3. Because 3 times 2 will give me 6 oxygens. 2 times 1 will give me 2. 6 oxygens here and 2 oxygens here equal 8. So that's perfect. And now we can look at the sulfur. We have 2 sulfurs here and 1 here, so we just put a 2 there. And we're done. Now, I know what you're thinking. You're thinking, okay, this is chemistry. There's got to be a better way to do this than just going back and forth and figuring it out. So, what is the algorithm that chemists use to balance reactions? And the answer is, this is what we do. There is no algorithm. There is no magic pill. It's brute force going back and forth and making sure everything matches. And sometimes it's important to do this. Count all the atoms up. How many sulfurs on the left? 2. How many oxygens on the left? 6 there and 2 there. How many hydrogens? 4. Over here, you see we have hydrogen, sulfur, and oxygen. How many hydrogens on the right? 4. How many sulfurs? 2 times 1, 2. When I say 2 times 1, I'm multiplying the coefficient times the subscript. 2 times 4, we have 8. And do these lists match? And the answer is they do, but this is a horrible way to compare 2 sets of things that you're hoping to make identical. So rather than do this, if you start with an SOH on this side, do an SOH on this side. 2 sulfur, 8 oxygen, and 4 hydrogen. So you can go 2, 8, 4, and they match. So if you are counting atoms correctly, there's no way in the world you should have a reaction that's not balanced. The caveat that if you're counting the atoms correctly. So are there any questions about this last one, letter C?
No, so using a fractional method, that's just kind of if it's a really large number or.
No, sometimes the fractional method can be used even for this one. So let me show you that, okay? But the fractional method is not something you normally want to go to. I'm going to leave the state off. So naturally, we've got the same number of hydrogens on each side, right? And we got the correct number of sulfurs on each side. So I don't want to mess with the number in front of this guy or the number in front of this guy. I only want to mess with that number right there. And let's call that number X. And this one is 1, and this one is 1, and this one is 1. Okay? I only want to change that number. Can we say that X times 2 plus 1 times 1 should be equal to 4? So here, how many oxygens do I have here? Well, X times 2. How many oxygens do I have here? 1 times 1. How many do I have here? 1 times 4. So I'm going to change this a little bit and call this 2x, because normally in algebra, we like to put the number first and the variable second, not the other way around. So we have 2x plus 1 is equal to 4. 2x is equal to 3. X is equal to 3 halves. So if x is 3 halves, we don't like this. So what are we going to do? We double everything. So 2, 3, 2, 2. Now, in this particular case, was using the half useful? I don't really think so. I think the brute force worked just fine, but sometimes the fractional coefficient works. Okay?
Yes, thank you.
We will see other situations where the fractional coefficient comes in really handy, okay? This is one where the fractional coefficient could come in handy. A. So the chromiums match, the chlorines don't. What number could I put here so I get 3 chlorines?
2.
No, 3/2,
Oh, shit, that's on.
right? Because 3/2 times 2 is 3. Now, do we like fractional coefficients? The answer is absolutely not. So how do we keep the ratios the same and get rid of the fraction? Double everything. Two chromiums, 3 times 2 for 6 chlorines, 2 times 3 for 6 chlorines, and we're good to go. So we could use the fractional method here, or we could use something else, which I call kind of a what do I want to say? Common factor, if you will. So we see that these come in 2s and these come in 3s, and we don't like that because one is even, one's odd. If we put a 2 here, we end up with 4 chlorines. That's no good, and so forth and so on. So what you do is you take these 2 subscripts and you find out what they both factor into. And the simplest way to find out what they both factor into is multiply them. 2 times 3 is 6. So our goal is to get 6 chlorines. How do we get 6 over here? Put a 3. How do we get 6 over here? Put a 2. And now if we have 2 chromiums, we put a 2 here, and we're balanced again by using a common factor, if you will. Any questions about A? Okay, let's go ahead and move on to B. So again, I like to start at the left and work to the right. I think you can see that we have 1 silicon and 1 silicon, so we're good to go. We have 2 oxygens and 1 oxygen, so I think we would like to put a 2 in front of the carbon monoxide. And we still have 1 silicon each. Here we have 2 oxygens, and here we have 2 oxygens. And then I go to carbon, and I have 1 here and 2 there, so I'm going to put a 2 there. So I want you to go ahead now and balance C, and when you're done, give me a thumbs up or something to let me know you're done. Right now, I'm trying to see if I'm recording.
It'd be easier if you move your arm so we can get the product on the.
Move it like that.
It's so hard when you're writing. I can't write as you're writing. I have to wait till you're done because I guess because you're are you left-handed? Yeah, it makes it really hard.
Actually, you can see what I'm writing while I'm writing it, but you have to close your right eye. Do you feel like you're getting taller? Because I'm pulling your leg. Of course, it doesn't work.
Yeah, I wasn't sure where it was going.
Now you know, next time I ask you, do you feel like you're getting tall? You know I'm messing with you. And if I say something about, oh man, my butt hurts, what does that mean? Means you're a pain in the behind.
Oh, I was just gonna say, been sitting for too long.
No, I tell my kids that all the time when they start bothering me. I go, oh man, my butt is starting to hurt. Okay, so I'm thinking a 3 here. What do you think? That look good? And then here we have 4. So I'm going to put a 4 there. And here we have 8. So I'm going to put a 4 there. How does that look? Okay. Okay. So we're done with that one. So we're supposed to balance the following and name each reactant and product. So let's actually name them first, and then we'll balance. So what do we call SF4? Silicon tetrafluoride.
Wouldn't that be sulfur tetrafluoride?
Oh, thank you. Sulfur. What would we call this one if we're using the naming method we learned in the previous chapter? Dihydrogen monoxide. So remember, for these things that are molecules, and we know they're molecules because they're all nonmetals, you name the first element first, use a prefix if there's more than one. You name the second element like an elamide, and you always use a prefix. So what are we going to call this guy, SO2?
Sulfur dioxide?
Precisely. And this guy here? Hydrogen. Mono, because you always use a prefix for the second element. And it's elamide, so fluoride. Okay. One sulfur, that's good. One oxygen, 2 oxygens, so I'm going to put a 2 in front of there. So we've got 1 sulfur and 1 sulfur. We've got 4 fluorines and 1 fluorine. I think we need a 4 over here. What do you think? We've got 4 hydrogens and 4 hydrogens and 2 oxygens and 2 oxygens. So we're good to go. So what are the names of the following? Instead of writing them down, I'm just going to say them verbally. Nitrogen trihydride. This one we just call oxygen because it's a pure element. Nitrogen monoxide. And this one we already saw, dihydrogen monoxide. Okay. I see 1 nitrogen on the left and 1 on the right, so that's good to go. I see 3 hydrogens on the left and 2 on the right. So this is one of those things where we've got kind of an even odd. And a lot of times when you have this even odd thing, you go for the smallest number that these are both factors of. So 3 times 2 is 6. I'm going to shoot for 6 hydrogens. So I'm going to put a 2 NH3. And I'm going to put a 3 H2O. Okay, so perhaps we need to revisit the nitrogen since we changed the number in front of NH3 and we already did nitrogen. So we can go back here and put a 2 to get 2 nitrogens. So now we need to deal with the oxygens. And here we have 2. Here we have 2 and 3 for 5 oxygens. So how are we going to get 5 oxygens out of this? And this is a perfect place for a fractional coefficient. So my question to you is, what number should we put here so that we get 5 oxygens? Five halves. Now, we don't like fractional coefficients, so what do we do to all of these? We double them. And now that we've doubled them, let's go ahead and take a moment and make sure that we're balanced. So N, H, O, N, H, O. 4 nitrogens on the left. 4 times 3 for 12 hydrogens on the right. 5 times 2 for 10 oxygens. On the right, 4 times 1, 4 nitrogens. 4 times 1 is 4 oxygens, but over here we have 6 times 1 for 6 oxygens. 4 oxygens plus 6 oxygens are 10 oxygens. And 6 times 2 would be 12 hydrogens. 4, 12, 10, 4, 12, 10, check, we're balanced. And let's take a look at C. How would we name each of these? One of them we would not know how to name. This one we can't name using our standard method because it has more than 2 types of elements. So we're not going to worry about naming that guy. This one would be boron trifluoride. This one we've seen before, it would be dihydrogen monoxide. And this one we've seen before over here, which would be hydrogen monofluoride. This does have a common name. It's called hydrofluoric acid. That's the common name. Okay. 1 boron, 1 boron. 3 fluorines, 1 fluorine. So I think I would like to put a 3 in front of HF. Okay. So I put the 3 in front of HF so that I would have 3 fluorines on each side. But now you can see I have a little bit of an issue with the hydrogens. Here I have 2. Here I have 3. But here I also have 3 hydrogens for a total of 6. So how are we going to get 6 hydrogens? We're going to put a 3 here. 3 times 2 would be 6 hydrogens. And then we check the oxygens. 3 oxygens here, and 3 oxygens there, we're balanced. Are we good to go? Okay, then let's go ahead and go. Do you still need that there a little more time there, Greg?
Got it, thanks.
Okay. So identify each of the following statements as either true or false. So this talks about equilibrium reactions. So let's talk a little bit about equilibrium reactions. They are reversible. So how do you know a reaction is an equilibrium reaction? Instead of one arrow, you have 2 arrows. I'm going to give you an example of a reversible reaction. This is called acetic acid. And because it is an acid, it can produce a proton, H plus. And what remains when we take away this H plus on the end is CH3COO. And if this is an H plus, this has to be a negative charge so that the charge is balanced. Because on the left, this is neutral. And on the right, these things have to add up to being neutral. So this can happen, but also this can happen. One of these guys can meet with one of these and make one of those. So this is a reversible reaction. This one that I'm going to give you is pretty much non-reversible. So when you're writing this one down, I want you to think about the answer to this question. How can we tell by the way this is written that it's not reversible? Single arrow, not reversible. That's the way we generally write a reversible versus a non-reversible reaction. Single arrow for non-reversible, double arrow for reversible. Okay, now, what does a reversible reaction mean? It means that in this particular case, you have this happening, but simultaneously, you have this happening. So both reactions are happening at the same time. We don't like writing both of them out this way, so we write it this way. So this is a reversible reaction. Now, the rate is how fast this is happening. So you've got the rate forward and the rate reverse. This is called the reverse rate based on what we've written up here. So I'm going to write forward up top and reverse on the bottom. At equilibrium, the forward rate equals the reverse rate. But the amount of reactants is not going to equal the amount of products. It could, but it's really rare. So when we talk about equilibrium, it's the forward rate equals the reverse rate. The amount of reactants does not equal the amount of products, but also the amount of reactants stays the same and the amount of product stays the same. So I'm going to give you an analogy of a reversible reaction, and it's going to be me and a millionaire. So I'm going to be the reactant and the millionaire will be the product. So do I have $1 million? No, I do not. The millionaire has $1 million. So we would say that the amount of product in this case is greater than the amount of reactants. Now, in a reaction at equilibrium, I would be giving the millionaire $1, and then the millionaire would be giving me $1. So if the millionaire gave me $1 and I gave the millionaire $1, how much would the millionaire have afterwards? And the answer is $1 million. We're going to say that this person is just right there to millionaire, no more, no less. Okay. What happens to my amount of money if I'm giving away $1, but I also get $1? Nothing. So the amount of money that I have stays the same. The amount of money that the millionaire has stays the same, but yet we're still having reactions go back and forth. So that's my analogy of an equilibrium reaction. Do you kind of understand that? So the idea there is that the amounts don't have to be equal, just like the millionaire and I don't have to have the same amount of money, but the rate stays the same. And because the rate stays the same, the amounts stay the same. Okay, so there's more about equilibrium reactions. Acid dissociation. We're going to talk about that. So an acid produces H plus in water. So this is an example of an acid reaction in water. And there's my H plus. And here's another example. So these are two acid reactions where they're producing H plus. And now I'm going to add something. Which one of these reactions is reversible, the top one or the bottom one?
Bottom.
Bottom one, definitely. Okay. So this is a strong acid and this is a weak acid. And the reason this is strong is because it's a one-way reaction. The reason this is weak is because it's reversible. So one way to think about this is that HCl likes to give up its hydrogen ion and H3PO4 does not. A really interesting thing is when you look at these formulas, this H3PO4 can actually do the following. So you'll notice I've written this product down as a reactant. This is an acid. So what do acids do? They make H plus. What's the other thing over here? Well, here's how we figure it out. This has 2 hydrogens. This has 1. So whatever is made over here has to have 1 hydrogen. This has 1 phosphorus. This has none. So whatever is made over here has 1 phosphorus. 4 oxygens, none here. So this needs 4 oxygens. And in addition, the charges have to add up. So above, H3PO4 has no charge. H plus has a +1. H2PO4 has a -1. +1 and -1 is 0. So what does the charge on this have to be so that this charge plus +1 is equal to -1? -2. This is a weak acid also. This is also a weak acid. So take a moment and take this weak acid and come out with the 2 products. When you're done, give me a little thumbs up. Okay. Excellent. So because it's an acid, it'll make H plus. And we're trying to figure out what the balance is. If we have 1 H here and 1 H here, we don't want any H's here. 1 phosphorus here, none here. So we're going to put a phosphorus, 4 oxygens, and the charge has to be -3. So when we look at these 3 acids, this one is weak, this one's weaker, and this one's the weakest of the 3. They're all weak acids. So a really interesting thing, though, is that when you look at this H3PO4, it can actually make 3 protons, 1, 2, 3, and give you a PO4. Can you see how this adds up to 0 charge? So the point I'm trying to make here is that look at this strong acid. It gives up 1 proton. Look at this weak acid. It can give up 3. The fact that it can give up 3 protons does not mean it's strong. Because we have to remember, in these cases, it doesn't want to give up the proton. This one-way reaction, it wants to give up the proton. So strong acids want to give up the proton. Strong acids are also called strong electrolytes, and weak acids are called weak electrolytes. And the reason they're called electrolytes is because it turns out that electrolytes are ions in solution. So strong electrolytes produce a lot of ions in solution. Weak electrolytes don't because it's a reversible reaction.
Tony, other than it being a reversible reaction, is that the only thing that makes it a weak electrolyte? Or is there
Yeah.
something else we can see?
Nope. That's what makes it a weak electrolyte, is because it's a reversible reaction.
Okay.
Okay. And there's a way to experimentally test if something's a strong electrolyte or a weak electrolyte. You make a solution of it. And if there's a whole lot of ions in there, and you put a light bulb in here and electricity to it, the light bulb will light up really bright if you have a lot of ions. And hence the name strong electrolyte. It conducts electricity really well. If you have a weak electrolyte, you put a light bulb in here, and what'll happen here is it won't light up really brightly, it'll be dim. So if you had H3PO4 in here, the light bulb would be dim. If you had HCl in here, the light bulb would be bright. And just to give you an idea of how weak these are, do you see this equilibrium right here? Do you remember my example about the millionaire and me? Well, this is worse. What I mean by that is there might be 100,000 H3PO4s, 100,000, and one of these and one of these. 100,000 to 1 and 1. For this second one, this might be 1,000,000 of these and 1 and 1. For the third one, it might be 1,000,000,000 of these and 1 and 1. So there aren't going to be very many ions in solution for these weak electrolytes. You should also know some strong acids and some weak acids. I'm just going to give you their formulas, and I'm going to make you responsible for looking up their names, okay? This is a strong acid. This is a strong acid. And this is a strong acid. You should know these three as strong acids. The following are weak acids. The interesting thing about this one is that's the only hydrogen that can make an H plus in solution. These three cannot. That's a weak acid. That's a weak acid. Plus there are more. For instance, this guy, if it gives up one hydrogen, it makes that. This is a weak acid. That's a weak acid. And that's a weak acid. Furthermore, this guy here, if it gives up its first H plus, after that, this is a weak acid. So these are examples of weak acids that you should be aware of. Interestingly enough, when you look at these acids, and I cover up the number of hydrogens, they look like polyatomic ions. If I cover up the hydrogen, it looks like a polyatomic ion. Do you kind of see that? Okay. Of course, the charge is not really there. And the thing about strong acids is that they, we say that they're product favored, because when that HCl does this, if all of these come apart, that means you basically only have product favored. And for weak acids, they are reactant favored. So reactant favored means you're going to have more on the left than you do on the right. So now you have the background where we can actually answer this question in number 14. All chemical reactions are product favored at equilibrium. And the answer is no. In fact, most of them are reactant favored at equilibrium. There is no observable change in a chemical system at equilibrium. So when they say chemical system, they mean that you're not going to see any change in the amount of any compound. And that's true. The amounts stay the same even if the reaction is happening. The example here is that millionaire who's given me $1 and me who's given the millionaire $1. There's no observable change in the amount of money each of us has. An equilibrium involving a weak acid and water is product favored, and the answer is no, it's reactant favored. Okay. Now I think we're going to quit there. Number 16, we didn't do this morning or this afternoon because it's in the book and I didn't want to look at it. This morning we did number 18, 20, 22, 24, and we did 26. So you might want to take a look at this morning's video to see 18 through 26. And we'll probably be starting with number 28 tomorrow. Actually, tomorrow's going to be about lab. But we'll start with 28 probably on Friday. And of course, you may want to ask questions about these on Friday also. All righty.
Okay, thank you.
You bet. We'll see you later, Isa. We'll see
All
you
right.
later, Greg.
Bye. Have a good evening.
Yeah, thank you for coming. I appreciate it. I really do.
You got it.
Yeah. Yeah, thank you for the questions. Bye.
Well, actually, I don't write these out. I actually have my daughter write them out. If you notice the handwriting here, it's quite different than mine.
Yeah, no, it's just helpful to go through the questions with you, it just forces me to start going through them.
Yeah, and I think that I'm hoping that my explanations help you to understand how to approach the questions, you know, how to think about them and so forth.
Yeah, it's helpful for sure. Thank you.
And I'm going to be honest that I do make it sometimes slow, but it's better that way usually, I find. Okay, I hope to see you tomorrow night.
All right, bye.
Bye-bye.